Hi, thanks for joining me today. I've got a problem from the Oxford University Maths Admissions Test. We are given a real number c between 0 and 1, and we're told that the line y equals c, this horizontal line here, intersects the circle x squared plus y squared equals 1 at two distinct points, here and here. And these 2 points, together with the points 1, 0 and minus 1, 0, form a quadrilateral, in this case, this trapezium here. We want to know which of the following graphs is a plot of the area of that quadrilateral against C. So we've been given 5 different options here, all of which have the horizontal axis as C, and then the vertical axis represents area. We want to know which of these 5 options best represents the area of the graph as a function of C. I will encourage you to have a go at this problem, and there's a couple of ways to do it, some easier than others. And in fact, the official solution here I wasn't a massive fan of because it isn't super elegant, but I will be presenting that solution and I'll explain why as we go through the solution. Okay, so the way we're going to do this is we're going to explicitly work out the area of this trapezium in terms of C and then dissect that function. So in order to do this, we need to first determine the x-coordinate of these 2 points up here, and that's pretty straightforward. We're just going to plug in y equals c into this equation here and rearrange for x. So we're going to get x squared plus c squared is 1, and rearranging this gives us x is plus or minus root 1 minus c squared. Cool. So that tells us that this upper length of our trapezium is going to be 2 lots of square root 1 minus c squared. And if we add that to the length at the bottom here, that's going to be 2, and divide that by 2, and then multiply by the height of this trapezium, which is just c, that's going to give us the area. And simplifying all of this gives us c plus c lots of square root 1 minus c squared. So this here represents the area of our trapezium. We can actually eliminate a couple of options from this, the main one being this guy here, option A, because when c is 1, the area of this trapezium is 1. Or as c approaches 1, the area approaches 1. So we can get rid of option A because that suggests that the area should be 0, but it's not. And we're left with 4 options here, and you can arguably eliminate E and B using the fact that this thing here is clearly going to be greater than C, because this thing here is positive, and you've got C plus a positive thing, and so it must be bigger than the straight line, kind of with gradient 1. And so this option E here has a curve that goes underneath this straight line, so you can ignore that. And this is just a straight line. So it's got to be either D or C, but it's not super clear how we can distinguish between the two, except for the fact that this guy here has a turning point. And so you might go, cool, let's just differentiate this, this function here and see where its turning point is. You know, what value of C gives it a turning point. If it's between 0 and 1, that's great. That means it's option D. If not, then it must be option C. However, for the mat, you're not expected to know how to differentiate something like this. And although if you did know, you absolutely could use that, the solution I'm going to present doesn't require you to know how to differentiate the square root of 1 minus c squared. Now, the way they did this in the official mat solutions, they kind of waved their hands a bit and kind of said that, oh, well, this thing here goes sharply towards 0 when c approaches 1, and so therefore this thing here must sharply approach c. This guy here doesn't sharply approach, sorry, not c, must sharply approach 1 as c approaches 1. This guy here kind of smoothly approaches 1, whereas this guy here you can see is kind of jagged and sharply approaches 1. And so therefore the answer must be D. But I didn't think that this was super satisfying. You know, how are you defining sharply? Why is it clear that this thing has to sharply be approaching C? It wasn't super obvious or super clear. So I'm going to be showing you something slightly else as to how we, or as another slight different way of deducing that the answer is D. And even the way that I'm going to present isn't super elegant, but it is a nice little trick that you can use for these sorts of problems. We're going to recall the fact that 6 squared plus 8 squared is 10 squared. So this is just as a result of the Pythagorean triple. And we're going to use this here because remember the mat is non-calculated. We're going to use this just to manually work out what the area value should be when c is 0.8. So since this is true, if I just divide this by 100, this equation, I get 0.6 squared plus 0.8 squared is it's just 1 squared. And now we're going to use this and just sub in c is 0.8 into this. So when c is 0.8, the area is just 0.8 plus 0.8 times the square root of 1 minus 0.8 squared. But that's just going to be, 0.6 squared. And therefore the square root of that is just 0.6. It's going to be 0.8 times 0.6. Now 0.8 times 0.6 is 0.48. And so altogether this is going to be 1.28, which is bigger than 1. And so this tells you that when the c value is 0.8, the a value, or the area, should be bigger than 1, 1.28. And so therefore that eliminates option C, because the asymptote here, or the value it approaches, is 1 from underneath, whereas here it clearly goes above 1. And so that eliminates option C, and therefore the answer is option D, which I believe is ever so slightly more elegant than this kind of hand-wavy worded approach that the mat originally presented in their solutions. Let me know what you think. I mean, I'm not sure if this is the most elegant way of doing this without using differentiation. Maybe you can let me know your thoughts in the description down below. Anyway, thanks as always for watching. I'll catch you in the next one. Have a great day.